Okay, physics module 14. We're going to do the notes. I am going to post a picture of my notes in the group me. So if you want to have a copy of the notes as I talk, since I'm not going to be writing everything on a whiteboard, you can print off the notes. I tried to write fairly neatly even, so bonus for you. I would recommend having the book open while you listen to the lecture so you can refer to the examples and follow along with those as we go. Okay, so this is talking about electric potential. And then the next module, we're actually going to talk about electric circuits and make circuits and do those things. So, a positive charge is attracted to a negative charge. That makes sense, right? They move towards each other. If things are moving, they have kinetic energy. So these are kind of things we just kind of have to think about as we're going to go through this. So, we have going back to our original thoughts of potential energy and kinetic energy. Remember, as you lose potential energy, you gain kinetic energy. So if you want to think of it as a ball, it's rolling down a hill. We did all those problems where we start with 0 kinetic energy and 100% potential energy. When we get to the bottom, we have 0% potential, 100% kinetic, and all along the way, we lose potential and gain kinetic. It goes from potential energy to kinetic energy. Okay, so here, same thing when these charges are moving. They are losing potential energy and gaining kinetic energy. So, all the kinetic energy has to come from the potential energy. That's where it comes from. The potential energy is kind of electric potential. It's not exactly, and we'll talk about the difference between that later. Okay, so your first equation is on page 257, the very first page of the chapter, and it's V equals K big Q over R. So V is our electric potential. This is just this phrase we're using of our electric potential. K is our Coulomb constant, and it is, we should have it already written down, it's 9.0 times 10 to the 9th. Q is the magnitude of the fixed charge. Be careful, your book, we found out this morning when I was doing problems with somebody, your book wants to try to confuse you by giving you charges when you don't need them. For the electric potential, the Q is the magnitude of the fixed charge only, not, or the stationary, either fixed or stationary charge, not the charge that's moving. R is the distance between the charges. Okay, it only depends on the charge that creates the electric field, which is why it depends on the fixed charge, because it's in one spot, it's creating an electric field. Our units are Newton meters over Coulomb, which is equal to a volt. This is not energy, it's voltage. Okay, so if you look at example 14.1, it is a very basic, straightforward problem. And it gives you do have to convert from microcoulombs, which just means times 10 to the negative third, and centimeters, because obviously these things are not going to be meters and meters apart. Surprised they're even centimeters apart. Okay, so electric potential energy, and the difference. Potential energy. So remember, we're talking about electric potential. It only depends on that fixed charge. Potential energy is going to be dependent on both charges. Therefore, our equation for that is on page 459. Potential energy equals little q V. So potential energy, PE is potential energy. Q is the magnitude of the non-stationary charge. It's the other charge that's coming into the field. And V is the electric potential that we found with the previous equation. So we use the previous equation to find the electric potential of that stationary object. And now we can find the potential energy using the Q of the object, the charge that's moving in, along with the electric potential of that charged object. Okay, so we find the electric potential, and then we can use the Q of the moving charge to find the potential energy. The unit of potential energy is joules because it is a unit of energy. If the electric potential increases, if you look at this equation, this will make perfect sense. If we increase the electric potential, our potential energy is going to go up. Okay, so potential difference. As a positive charge moves towards a negative charge, the potential energy is going to decrease. This should make sense. So if we have a stationary charge here, and this charge starts moving towards it because it's attracted, positive and negative, they're attracting each other. This one's stationary, so it can't move. As this one moves, it loses potential energy. That should make sense because if we're moving, we lose potential energy, right? Potential energy is the ability, the stored energy. Once we start moving, it converts to kinetic energy. So we start moving, our potential energy goes down. It becomes more negative. A negative charge approaches a negative charge. So if this one's negative and this one's negative, and they start to approach each other, the kinetic energy is going to go down. Why? Because they're repelling. They're going away. This one can't move. It's going to repel. It's going to actually move the opposite direction. If we're moving opposite direction, our kinetic energy has to go down. The change in potential energy is determined by the change in electric potential. That's determined by this guy here. Remember, electric potential has to do with the charge of the stationary object and the distance. So as the distance changes, our electric potential is going to change, and our potential energy, therefore, will change. Okay, so if we look at example 14.2, so this one gets to be a little longer, right? Because we are given a charge, a freely moving charge, and we're given a fixed charge, and we're given a distance, and then we're given a new distance, and what is the potential energy change? So the first thing we need to do is find the electric potential. Remember, again, the electric potential is the stationary object, and then the distance between that and the moving or the not fixed object, the one that can move. So you find the initial with the distance. Find the initial potential, electric potential, which in this case works out to be 6.4 times 10 to the 7th volts. Please make sure you kind of check on your calculators that you can enter the scientific notation correctly, because there's been a few mistakes on that on quizzes and stuff. Check that you're entering all of that correctly in your calculators. Now, once we have the initial, now we have a second distance. This charge is still the same, but our distance now has changed. So we find our final electric potential, which again is labeled V. I know, I wish they used some different letters, but it's labeled V. And so we find that, and it works out to be 8.2 times 10 to the 7th volts. So to find our change in potential energy, we know the little q is the moving charge of the moving one, and we know the change, we know the initial, and we know the final, so we know the change, therefore. And we can plug those into our equation and get our final potential energy, which should give us -1 times 10 to the 5th joules. It should make sense that the potential energy is negative because we're losing potential energy as they're getting closer, because we'd be gaining kinetic energy. An electron volt, electron volt is the decrease in potential energy when an electron moves through a potential difference of 1 volt. So electron volt is the decrease in potential energy when an electron moves through a potential difference of 1 volt. And this is how batteries are rated. Whether you have 1.5 or a 9 volt battery, it's the potential difference within the battery. Okay, conservation of energy and electric potential. So if you look at, okay, hold on, we'll wait before we go. We talked about potential and kinetic energy are in the system, like in that system, the total energy has to stay the same. So the total energy is our potential and our kinetic. So if potential energy goes up, kinetic energy goes down. If potential energy goes down, kinetic energy goes up. Probably tired of me saying this, so hopefully we can remember that. Okay, so if we want to find the velocity of this moving thing, this moving charge, we can if we find the kinetic energy. How can we find the kinetic energy? By finding the potential energy. So if you look at example 14.4, we have a negative 2.3 microcoulomb charged particle, gives the mass of it, is placed 1.5 meters from a positive 1.8 microcoulomb stationary charge. If the particle starts at rest, how fast will it be moving after it's traveled 75 centimeters? Okay, so we know how far it is to start with. So we can find our initial velocity, or I'm sorry, our initial electric potential. Our initial electric potential, V, equals KQ over R. We know K is a constant. Q is the stationary charge. And then the distance between them is 1.5. We find that. Then we can find our final because we know the new space because it's moved 75 centimeters, which means we're now at 0.75 meters because 1.5 minus 0.75 is 0.75. We plug that in and we get the final. We subtract those two. We subtract final minus initial, and we get a change in our electric potential of 1.1 times 10 to the 7th volts. Now that we have our change, we can find our potential energy. If we know the potential energy, the change in potential energy is negative 2.5 times 10 to the 4th. It lost negative 2.5 times 10 to the 4th joules. If it lost it, that was gained by kinetic energy. So the kinetic energy is 2.5 times 10 to the 4th, and then we plug in 1/2 the mass times V squared, and we can go ahead and calculate V, which is our velocity. That is velocity because it's little v. Okay, so it's really about that potential and kinetic energy situation of when we're losing potential energy, we're gaining kinetic energy. Okay, a capacitor. What is a capacitor? It's a device that stores energy. Charges are brought together and forced to stay and creates electrical fields. So they show you a picture of a parallel plate capacitor, and there's a distance between them. Now, I'm going to recommend you read over the lab. Normally, I would say you could skip labs because we'll be doing them. We won't be doing this one because it does require a balloon, and we can't use a balloon. So read through the explanation of the lab. I mean, kind of read through the basic details of the lab. Look at the picture. You don't have to read every single detail. But read through the explanation of the lab so that you can kind of understand how a capacitor works. I might try to find a little video on capacitors. That would probably be a good plan. Okay, so we have a new thing called capacitance, which is C with a little q on it, capacitance. So V equals Q over CQ, capacitance. So this is our equation on page 472. V in this case is electric potential. Q is the total positive charge stored in the capacitor, and CQ is capacitance. What is capacitance? It's how much charge a capacitor can hold at a given voltage. If we increase the capacitance, it can hold more charge. Okay, and then example 14.5 shows you how to find that. And then we talk about an application of this. Can use a capacitor to create an electric potential in a set area. So a free moving charge experiences a change in electric potential as it travels from one plate to another within a capacitor. Negative to positive, it causes increased electric potential. Positive to negative causes a decrease in electric potential. And then it goes through example 14.6. Okay, and then at the very end, it talks about how a television works to make its picture. So you can... This is not actually probably how TV nowadays works. This is probably how a cathode ray tube TV worked. You used to be able to replace the tubes. That's why TVs used to be so ginormous, is because they actually had these tubes inside of them. Okay. So, let me know if you have any questions. Like I said, I will post the pictures of the notes for you also.